Good morning and happy Monday. Today the internet on campus around 8 o'clock started to go out, and even when it did come back intermittently, I was able to get into Teams but not open anything, and even including sharing my screen. So we're going to try a different approach to ensure that we don't get behind with learning. I am here on campus to answer any questions. Again, our only downfall right now is ensuring the internet is working, but I do have my phone available. Unfortunately, I didn't bring my charger today, and so that is a downfall that maybe by the second period it will already be dead. What you're looking right now was the assignment that was provided to you last week, and I asked you on Thursday to complete this, and so I just wanted to review how does this look and how does it tie into what we're going to learn today. So we had different learning objectives. The first three problems that you can see here, our goal was to rewrite these problems and then simplify. And notice they all had radicals in, and they all were expressions because we saw no equal sign. Then 5, 6, and 7 had radicals in, and we wanted to rewrite them so there's no radical in the denominator. So again, this was going to be simplifying. We're going to rewrite it and then simplify the radical expressions, 5, 6, and 7. And then again, the same type of learning objective, just a different look to the problem. These are all expressions because there's no equal sign. We do have radicals again, and our goal here was to rewrite this. We used Desmos here to help us out in doing the calculations, and we wanted to rewrite it so we had no radical in the denominator. But the most part I want to show you here is that we had multiplying. When we did have two things that we were trying to simplify and combine, it was multiplying, and we had the same nth root. Multiplying, the same nth root. Multiplying, the same nth root. And remember, when you don't see an nth root, it's actually a 2. Well, how does that relate to what you're going to be learning today? Well, today we're going to do two problems in your class notes that look kind of similar to those three problems you had in homework. But instead of multiplying the two groups, we are either adding or subtracting. And I'm going to add a little twist here. It's the same way that I've taught it maybe for the last 10 years. It's not necessarily something that if you look into Khan Academy, they're going to use the same terminology. But I found that this little method often helps students understand this better and make it just a little bit simpler problem to do. Feel free to press pause in this video at any point when you need to keep up with writing things down. So here's our very first problem. We want to find a way to rewrite this and then simplify it. Rewrite it and then simplify it. All right, so the first thing I'm going to do is I'm going to look at this expression and say, is it even possible for me to simplify it? And it is, because although I have radicals in each part of the expression, so this is term 1, term 2, and term 3, there is a radical in each one. The key is they have the same nth root. So that gives me hope that I am able to simplify this further. What if they didn't have the same nth root? Okay, we stop. We can't simplify it any further. Maybe we can break down that particular radical, but we can't combine them. They cannot be combined if they don't have the same nth root. Okay, so that's your first step. Your second step is to look at when I grab a highlighter here. When I look at the radical in each of the three terms, I need to come up with a strategy of how I can break this down. So I start by looking at the smallest number inside of the radical house. And it happens to be 3. That's the smallest one. Just like if we look over here, the smallest one inside is a 2. So the smallest number is a 3. And how is that going to help us? We want to find a way to rewrite this so that it has 3 times something. And this is going to be 3 times something. Now, how do I determine what that number should be? Again, notice that the nth root is 4. So I'm going to go to the fourth. Remember, this is the table I asked you to write down in your notes. If you need to go back, that was already provided for you, that video. Go back and write this down. You're going to use that throughout this entire unit. So I go to the fourth column because it has the fourth root. And I ask myself, okay, so I know I want to rewrite this with a 3. Can I take 3 times some number in this column? Can I take 3 times some number in this column and end up with a 48? Again, why am I choosing 3? Because it's the smallest number. And why am I choosing this column? Because the nth root is 4. Now, if you're pretty good with multiplying, you may go, yeah, you can. In this column, I know that 3 times 16 is 48. Awesome. And you may go, oh, I know 3 times 81 is 43. Or maybe you're honest with yourself and you're like, yeah, I'm not that good. Okay, so if that's the case, you're going to go over to Desmos, and we're going to take, let me come back so you can see this. We're going to take this 48 and we're going to divide it by 3 to see, do we get a nice number? Thank you for your patience. Here we go. 48 divided by 3 is 16. Okay. Notice there's a 16 right here. Nth root is 4. I go to the fourth, so that tells me 16 times 3 is 48, so I can rewrite that. Let's do the same thing. Let's take 243 and divide it by 3. So I'm going to change this to a 243, and it's 81. So 81, which is also in this column, 81 times 3 is 243. So when I rewrite this, that's what I'm going to do next. I'm going to rewrite this as 5. It doesn't matter which one you write first. I'm going to start with 81 and 3. They get their own radical house, we'll call it, and they both have to have an nth root of 4. 81 times 3 is 243. That's this first term here. Then there's a subtraction sign. This is the second term. I'm just doing this so you can kind of see the breakdown. It's not as overwhelming to look at. And here's the third one. Remember we said that 16 times 3 we were able to determine was 48. 3 terms in the original expression. Here's the 3 terms when I'm rewriting it. What is the next step? Let me grab a colored pen. 1 second. Now, what was the reason for us doing this? Why did I rewrite it? I rewrote it in a way that allowed me to break it down further or simplify it. So I go into the fourth column and I find 81 again. Fourth column and I find 81 and I go all the way across and notice it's equal to 3. This is equal to 3. Same thing here. I rewrote 48, so I find 16 in the fourth column. I go all the way across and it's equal to 2. This is equal to 2. So when I rewrite it, I have 5 up front. Now this is rewritten as 3, and then I have 4th root of 3. Subtract 9, 4th root of 3, plus 2. And now this is equivalent to 2 times the 4th root of 3. Now here comes Miss Bradley's little technique that it's not something that's mathematically you would just look up. I'm just going to use any symbol. I'm going to use star. It's easy to write. And I'm going to call what they all have in common star. Is it necessary? Nope. I just found that a lot of students at this point struggle to know how to combine like terms. So this is 5 times 3. Students know that. And then I'm going to call this star. So I have 15 star, subtract 9. There it is again. Subtract 9 star. 2 times 2 is plus 4 star. Okay. 15 subtract 9. 15 star subtract 9 star is 6 star. 6 star and 4 star combined to give you 10 star. But remember, it's not really star. That's just Miss Bradley's kind of silly way of rewriting the 4th root of 3. So I rewrite this as 10 and then 4th root of 3. This is the final simplified answer. This is equivalent to this large expression. Again, press pause, go back and rewrite this in your notes. The second problem today in your notes. Similar to the first one, we have 3 different terms. There's 1, 2, and 3. And I noticed that they all have a radical in. Specifically, they have a cube root, the third root. So that tells me that I should be able to go further with this and simplify. And I find the smallest one inside of the radical house. So there's a 16, a 2, and a 1024. So 2 is the smallest. And now I'm going to look into the third column. So instead of the fourth column now, we're looking in the third column. And I'm going to ask myself, 2 times what is 16? Is that possible? 2 times 8. Okay, is 8 in this? 8 is here. So I can rewrite this as 15. And then I rewrite the 16 as 8 times 2. Don't forget to put the little cube root out front. Make sure it's small. And then we have 8 times 2. Now, it doesn't matter if the 2 goes first or if the 8 goes first. It doesn't make a difference. But this is rewriting the first term. Here's the second term. It doesn't have to be rewritten because it already has a 2. Remember, my goal is to have a cube root of 2 in each term. And then the last one, I already have a 2. Now I have 1,024. I look into the third row. I'm looking at all these numbers, and remember, the key is 2. 2 times something here would equal 1,024. Well, like, for instance, I know 2 times 125 is not 1,024, and I just keep going. Like, oh, maybe this number, 500 times 2, may be really close to that. And so if you can't do that in your head, you come over here and you go 512 times 2, whoops, excuse me, times 2, it works. It's 1,024. So when I come back, I know 2 times 512 is 1,024. So there's 2 and 512. Again, common mistake is students forget to put the cube root here, and again, it doesn't matter which one goes in front. So here are the 3 terms, and I've rewritten 2 of them. Now, what is the purpose of rewriting? Why do we do that? We do that so that we can continue to simplify further. For instance, I take anything that's not the cube root of 2, in this case it's 8, and I find it in the third column. I find the 8, I locate it, and I go straight across, and I go, oh, that's actually equals 2. This is equivalent to 2. Anything that's not the cube root of 2, that'd be 512. So I'm looking for the cube root of 512. So go into the column of 3, find 512, go across, and it's equal to 8. Don't be afraid to rewatch this a couple times. It's not uncommon for students to feel really confused about this. So I'm going to rewrite this. I have 15 times 2 times the cube root of 2. Subtract 8 times the cube root of 2 plus 2. And I'm going to bring this 8 in front times 8. And there's the cube root of 2. Now, do you have to use this method I'm showing you? Absolutely not. But I'm going to say that star equals the cube root of 2. So 15 times 2 is 30. So I have 30 star minus 8 star plus 16 star. And you know from prior math that we can only combine when they have something in common. In this case, it's the star. 30 subtract 8 is 22 with the star. And 16 star combined with 22 star is 38 star. Well, we can't leave it like that. We have to replace star with what it really is, and it is the cube root of 2. Press pause and go back and please write down. Let's review for a second before we move on to solving equations that contain radicals. Let's review what we know. When we see a radical like this, remember that if you don't see the nth root, it is a 2, and it could be rewritten like this. This is called rational, which means fractions, rational exponent form, and this is radical form. Now, what we do know about square roots. So, square roots are a type of radical. Square roots are one type of radical. So here's like the radical umbrella. These are all radicals, and square roots are just one type. They're just one type. Well, what else could there be? Remember, there could be cube roots, be to the 4th power, 5th power, this endless number, okay? So square roots are just one type, but square roots up until this point in your math career is the only type of radical you've ever worked with before. And so what you know about square roots is this. No matter what number I provide you, if I said, well, tell me about the answer of this, and you're like, well, I don't know. We know that this number inside can never be negative. Remember, we learned that we can't have a negative inside. You may think that I'm contradicting what I taught you in Unit 3 because although we can evaluate this, remember we learned this year that we can pull that negative out front, it becomes an I, and now we have 4i. It's an imaginary number. But without taking the negative out front, we cannot take the square root of a negative number. Square root is key. What else do we know about the answer that we get? We know that the smallest number we can get is 0, and then it's 0 or above. So the answers that we get will be greater than or equal to 0. Greater than or equal to 0. Okay, so I'll give you an example here. If we know we can't plug in a negative number, then the largest number we could plug in is 0. The square root of 0 is 0. The square root of 1 is 1. The square root of 4 is 2. The square root of 9 is 3. That doesn't mean we can't take the square root of 2 or 3 or 5, 6, 7, 8. It just means that the answers we get would fall between 1 and 2 and they'd be ugly decimals, or they fall between 2 and 3 and they'd be ugly decimals. But this shows us that the answers that we're going to get from square roots are always 0 or above. And the reason why I'm sharing that with you is because the next problem we do, knowing that fact could save you a lot of time. So here's the first problem. If you could write it down, please. We're going to solve this radical equation. And so we're going to do PEMDAS backwards. Please excuse my dear Aunt Sally. So on the side that contains the variable in this case is an m. On the side that contains the m, I'm looking for anything on this side that has adding or subtracting, outside of the radical, of course. And so I'm going to do the opposite operation. So opposite of adding and subtracting. And positive 231 and negative 231 combine to give you a 0. That happens on the left. On the right, they combine to give you 4. And then, so I'm taking care of adding or subtracting. That's outside of the radical. Now I'm going to move on to MD, multiplying and dividing. Remember, you don't multiply first, you don't divide first, you do whatever you see from left to right. So to get rid of this multiplying, because really it's negative 1/4 times this quantity, normally we'd say divide by negative 1/4, and there's nothing wrong with that. But you learned in 9th grade that when you have a fraction, to eliminate it from the left side, really it's going to reduce to 1, but to eliminate it from seeing it on the left side, we can multiply by the reciprocal. Reciprocal means just take what you see and flip it. It means don't change the sign, just take what you see and flip it. Now a lot of times we go 4 divided by 4, it just disappears. Well, again, this year I've tried to tell you that really it does, 4 divided by 4 does reduce to 1, and 1 divided by 1 reduces to 1. But a negative times a negative becomes a positive. So yes, we don't see anything left on the left, right? They do disappear, but I want you to understand the reason behind that. And now we have the square root of some quantity inside is equal to negative 16. Now here's where understanding square roots could save you like 2 to 3 minutes, maybe up to 5 minutes. This says whatever the value is inside, when you take the square root of it, whatever the value is inside, you're going to end up with a negative 16. Well, if you understand square roots, the key is it's a square root. Remember, if you don't see the number out here, the nth root, it's a 2. If you understand square roots, you know that the largest value you can have on the opposite side is 0. So this should only equal 0 or above. Well, what if it equals a negative? Then the answer is no solution. You could literally write down, I know the square root cannot equal a negative number. No solution. That would be acceptable. But for the majority of you, you're working hard, you're trying to do PEMDAS backwards, and you may forget that. So what do we do then? You're going to square the left, and you're going to square the right. And when you square this, those cancel out, and you have 5m plus 16 equals 256, a positive 256. Then you subtract 16 from both sides. 56, excuse me, I wrote that wrong. Subtract 56 from both sides. And you end up with, I'm going to come over here, 5m equals 200. Now the math steps I did after I corrected the 16 into 56, everything I did algebraically looks great. I get an answer of 40. But if you forgot this fact, then how can we know that the answer is no solution? Okay, well then you always have to take this and you have to check for extraneous solutions. That means when I plug in 40 into the left-hand side of this equation, I'm going to type this into Desmos. When I plug in 40, I better get a final answer that's equal to 235. If this answer doesn't equal 235 when I substitute in 40, it means it's extraneous. So I'm going to do that right now. So I'm going to type in right now. There was a negative 1/4 out front. Excuse me, let's make this a little bit easier here. Then it was the square root, and it was 5 times 40 plus 56 and plus 231. Okay, so I did all of the work by substituting 40, and Desmos calculated an answer of 227. That means this side is equal to 227. The right side is 235. They're not equal, which means this is an extraneous solution. When there's no other answers and you get extraneous solution, if there's nothing else there, then the answer is no solution. So whether you are able to recognize it at this step and you explain and write no solution, or you do all the math and go back and check to determine no solution, is really up to you. I'm going to go on to the next problem. Next problem looks a little different, and that's because now we have two radicals. Two radicals, the nice thing is they are on opposite sides. They're on opposite sides of the equation. And I personally like to rewrite these. It's not required, but I like to rewrite these in rational exponent form. So remember, when there's a 3 here, it doesn't mean I put a 3 on top. It's a 1/3. You may be thinking, well, why do you do that? It seems like extra work. Just for myself, I prefer that form. And now, when I want to find a way to eventually solve for x, I ask myself, what do I need to raise these to in order to eliminate it? Whatever you do to one side, you must also do to the other side. So I'm going to raise it to the reciprocal of 3 over 1. And I get 3 over 3, which reduces to 1. 3 over 3 reduces to 1. And I get to bring down 2x plus 5 equals 5x plus 32. And now I just solve it like normal. Choose to move the x's to one side of your choice. Negative 27 equals 3x. Just because you get an answer that's negative, that's a misconception, doesn't mean your answer is wrong. But after every answer, you have to plug it back in to see if it's correct. So I'm going to come back up here. I'm going to substitute in negative 9, and I'm going to see if this is correct. Now, how do I write this in? You're going to watch that. So I'm going to substitute in negative 9 now, and I'm going to put it in this form. I'm going to put it in this form and substitute in negative 9. Here we go. So inside was 2, and then the number was negative 9 that I was able to achieve, plus 5. Now I'm going to raise it to, if you come down here, you'll see the a to the b. I'm going to raise it to the 1/3. Oops, excuse me, 1/3. Okay, so I get a really ugly answer here. Negative, I'm going to write that down. I get negative 2.3513, blah, blah. Okay, that's the left-hand side. If this is truly the answer, and I was able to get this ugly answer on the left-hand side, when I substitute negative 9 in for the right, I better get that same ugly answer. So now I'm going to type this in, inserting negative 9. Okay, this is 5, negative 9, plus 32. Okay, I'm going to write down that answer, negative 2.3513. And I can see the two answers are the same on the left and right. That means negative 9 is the correct answer. Going on to the next problem. Okay. So there's a couple different ways to go about solving this. Remember, our whole goal is here to find an x value so the left side equals the right side. The first thing we often like to do, just like we did in the last problem, is let's get rid of that radical. Let's get rid of this radical. So right now we know opposite of square root. Now how do I know it's a square root? Because there's a hidden 2. if there's any other nth root there, you would see it. So opposite of square root is a square. So I'm going to write down the problem, and then whatever you do to one side, you have to keep it balanced. You must do to the other. I'm going to square the left. When I square the left, I must square the right. So what happens in the left are these two cancel because they're opposite operations, and I bring down 6 minus 5x. Now this next part is a really common misconception. This means write this twice. This means write this down twice. So it's 2x and 2x. Write this quantity twice. Okay, so once you see that, most students are able to go 4x squared. Now I'm going to move everything to the side that has an x squared, just my preference. When the negative 5x moves across, it becomes positive. And when the positive 6 moves across, it becomes negative. Remember, we've learned this year that when we have quadratic equations, we can solve by factory sometimes, and when we can, it's a lot easier. We can always solve using completing the square or quadratic formula. That's up to you. So I'm going to check to see, is this factorable? 4 times negative 6 is negative 24. I'm looking for two numbers that multiply to equal 24 but combine to give me 5. 8 and negative 3. I want to check. Yes and yes. Okay. So x plus 8 and x minus 3. Now, a lot of students, you're working so hard, you're showing all your steps, you get to this point and you forget, and the leading coefficient is different than 1, you've got to put it underneath. Now here's the reason why I like when I can factor. Because when I can factor and I get to this form, it's pretty easy. I don't have to do bottoms up because I'm trying to solve. One answer, I'm going to come over here, is negative 2. Now this is before I check for extraneous solutions. One answer is negative 2. One answer is positive 3/4. Remember, it's opposite negative 2 and positive 3/4. Now how do I know which one is the correct answer? So I'm going to teach you right now another method that we can do to check to see extraneous solutions. So this is the original problem, and I'm checking to see which one of these is right. Are they both right? Is only one right? Are they both extraneous? So here's another teaching tool that I'm going to provide you with. Okay, so if I come back here, just to give you an idea, I'm going to graph this, y equals this, and I'm going to graph this, y equals this. So think of this as an equation. Y equals square root of 6 minus 5x, and y equals 2x. This is one equation, this is the other equation. I want to know, where do they meet? Wherever they meet, whether it's in one place, two places, or never, will tell me the actual answer. So y equals 2x was 1, and then y equals the square root of 6 subtract 5x was the next. Okay, so I'm going to pull this back, and I can see that they meet in only one place. That means there's only one answer. Now when I click on it, I may be asking yourself, well, which one is the answer? Is it like 0.75 or is it 1.5? If we look back to our problem is trying to solve for x. So when I look here, think of this. Which one of these represents the x? And it's the first number is the x. That means there is only one answer because they only cross in one place, and that x answer is 3/4. So without doing any other math, I'm able to say this is the actual answer and this is an extraneous solution. It doesn't mean it's extraneous because it's negative. That's a misconception. It means because they never cross at the point where x is negative 2.